Okay, so we are ready.
Okay.
Okay, so let us go back to our last lecture. So we discovered that an important concept in the applications is that of metric space. Okay, and we discussed the concept of distance between shapes of an Euler-Bernoulli ring. Okay, we said that. Let us repeat this because we had a discussion about infinite dimensional configuration spaces and finite dimensional configuration spaces. So we said that a rigid body is a mathematical model in which the configuration of the system is given by a point in R3 cross S2 cross S1. This is the sphere embedded in 3 dimensions. This is the circle embedded in 2 dimensions. So that 6 parameters are enough for describing the configuration of a rigid body. A material particle has a configuration in R3. We discussed the different models which we can introduce for the Earth, for instance. And so we said that in the motion around the Sun, this is enough if you want to describe the phenomena of motion of the Earth around the Sun. And this is required if you want to study the alternance of seasons on the Earth. So for describing some phenomena, you need a richer model. For describing other phenomena, a simpler model is enough. However, when you have a beam, and also in the simplified case of transverse displacement, which is the simplest one you can deal with, even when you consider this simple case, the space of configuration is made of functions. Okay? So we started considering functions u belonging to C0. Okay? And what we discovered that this vector space, because C0 is a vector space, you can add 2 C0 functions, you get another C0 function. You can multiply a C0 function times a scalar, you get another C0 function. You have the opposite of any C0 function. You have a 0 C0 function. So this is a vector space, verifying all axioms defining a vector space. Okay. This vector space is infinite dimensional. What we have found a sequence of C0 functions. The constant function, the function which maps every real number into 1. The first order homogeneous polynomial up to the nth order polynomial. And then you go on. So you get a sequence of C0 functions which form a set of linear independent elements of C0. The cardinality of this set is the cardinality of natural numbers, so it is a numerable infinite set, and they are all inside C0. So there is no chance to represent every vector in C0 as a linear combination of a finite number of elements of C0. Okay? So the big difference between the mathematical models which use a finite number of parameters and mathematical models using an infinite number of parameters consists in the fact that in these two kinds of models there is a vector space which is involved. In one case it is finite dimensional, in the other case it is infinite dimensional. Of course you can tell that S2 is not a vector space and S3 is not a vector space, but I told you that S2 is embedded in R3 and S1 is embedded in R2. Okay, so you have a vector space R3 Cartesian R3 Cartesian R2, and our space of configurations is included in this finite dimensional vector space. Okay? So, in a sense, this is the finite dimensional vector space in which our space of configuration is embedded, is included, and this space of configuration inherits many properties of this vector space. Okay. The bad news is that in this description of reality, in this model of reality, you are obliged to introduce a vector space which is infinite dimensional. Okay? Now, we must try, by the way, I found a book which is written in English and it is very clear by a Russian author, two Russian authors. It is very typical of Russian school to develop mathematics with a strong view towards applications. So it is a book in which you find for every novel mathematical concept a motivation from the applications, which is rather rare in other schools. Okay. So I think that this book, by the way, it is freely available on the web. You even don't need to go to LibChat. You find it rather easily. Okay. So,
can you say
name of the book?
Look, I forgot. Lebedev is the author, but we have all your mails. If there is, you should give us new mails. We will send you all documents, so you will have it. Of course, it is a big book, but you are old enough to be able to select. I remember my professor of theoretical physics gave us big books, and when we took all of them, I calculated, he gave us 3,000 pages. So I told him, how can we read all of this? And his answer is what I tell you. It is your capacity to select those pages which must be read. Okay? So, I will give you not 1,000 pages, but though many pages. So you will have those pages which you read for this class, and you keep your book, this book, for future reference. Remember that everybody among us has a library to which he has to refer. Don't throw away books when you have used them. You must keep them in your as a PDF now in your computer. I still have books in my shelves, the physical one, in paper. Okay, so let's go to our discussion again. So we understood that in order to deal with finite dimensional and infinite dimensional systems with a unique theory, we have to introduce the concept of metric space. And we introduced the concept of metric space in the last lecture. Then we discovered that there are metric spaces in which you have Cauchy sequences which are not converging. So let us remind what is a Cauchy sequence. You have a sequence xn inside S. It is a Cauchy sequence if for every epsilon greater than 0 there exists a capital N such that n greater or equal to capital N and k greater or equal of capital N implies distance between xn and xk smaller than epsilon. A Cauchy sequence is a sequence in which, starting from a given n, all the elements of the sequence are closer than epsilon. So it is clear they want to converge. They would like to converge. Okay. Their aspiration is, I want to converge. However, by the way, if xn is converging, then xn is Cauchy. So in general, the set of Cauchy sequences is bigger than the set of converging sequences. Okay? So, if a Cauchy sequence wants to converge, but square root of 2 gives you an example of rational sequence of rational numbers which is not converging. We did this discussion last time. So we said if I find a sequence Q1, Qn of rational numbers approximating from below and P1, Pn, another sequence of rational numbers approximating from the upper approximation of the solution of x squared equal to. You can find two sequences like that, such that Pn minus Qn absolute value is smaller than 1 over 10 to the power n. So they are becoming closer and closer. Qn is increasing. Pn is decreasing. So, one is going down, the other is going up. Everything indicates that they should converge. However, we know that square root of 2 is not a rational number. So, what we can conclude? We can conclude that Q with the matrix D defined in this way, Q minus distance between P and Q is equal to the absolute value of P minus Q. Q with this distance is not complete. In the sense we have said last time. We call a complete metric space a space such that Xn is converging if and only if Xn is Cauchy. So usually the set of converging sequences is smaller than Cauchy sequence. If a metric space is complete, then the two concepts coincide. Okay? So to know this implies that there is a limit of the sequence. Okay? And we know that there are spaces which are not complete. Q with the standard matrix is not complete. So in a sense, Pythagorean were proving the fundamental result that Q is not a complete metric space. Okay? Okay, so this is for resuming what we already said another time. Then we started talking about further ideas, and now we try to give more details about these further ideas. So, why we are so interested about completeness? We are very much interested about completeness because usually you try to solve a problem building a sequence of elements in the set where you are looking for the solution, and this sequence you want to approximate the solution. This is a standard procedure. Just to give you an idea, imagine that you have a function. Function like that. Okay. What you want to solve the problem. You imagine the function is C0 and even differentiable. Then what you want to do? You want to try to find the zero of this function. So the element of its domain where the function is vanishing. Okay? Then you may have the idea, okay, this plot is not very good, for some reasons you will understand immediately. We can do something later. So, how you can do for building a sequence of points in the domain which is converging to the value x0 when the function is vanishing. You can take one point, you call it x1. You can calculate f of x1. This is so-called Newton procedure. Then you can take the tangent to the, so what is the tangent? Is a straight line which is passing in the point x1 f of x1, having as a angle, so the characteristic, I think we call it in English also angular coefficient of the tangent. Okay. This angular coefficient is exactly the derivative of the function f in x1. So what do? You write the linear approximation of the function, so the Taylor expansion of f in the neighborhood of x1, which is this one. Of course, this is different from f of x. If you look to this plot, they are close here, but they can be very different. However, this function is linear. So you can solve very easily the problem this linear function equal to 0. And you can say that x2, the next approximation of the 0 of the value of x where the original function is equal to 0 can be calculated out of this equation. So you can say that x minus x1 is equal to minus f x1 divided f prime of x1. So you find x2 like this. Okay. Then you can calculate x3. You can calculate x4, and so on. Okay? And you hope that this sequence is converging towards the solution of your problem. F of x equal to 0. Okay? Now, what can you calculate? The elements of the sequence. You cannot calculate the limit in general. There is no algorithm calculating the limit. Okay? You agree with this? So what you can estimate? The remainder. In general, you can calculate xn plus 1 minus xn. Absolute value. This is what computers are calculating. And what is very courageous, you say that the sequence is converging when this difference becomes smaller and smaller. This is what computers are doing. They calculate this remainder. Okay. Imagine that your space is not complete. The fact that this difference becomes smaller and smaller does not mean anything. It could be that the limit is not existing. Even if this correction, one step after the other of the algorithm, is becoming smaller and smaller. So you understand the frustration of Pythagoreans. They had proven that their sequence was having a remainder which was smaller and smaller, but they could simultaneously prove that the limit is not a rational number. This was a conceptual shock. I repeat you why. Essentially because Pythagoreans believed that all quantities were rational numbers. So, as they confused the concept of quantity with the concept of rational number, they believed to have proven that in reality the hypotenuse of a rectangular triangle with cathets, isosceles triangle with cathets equal to 1, 1, they believe to have proven that this hypotenuse is not existing. You must understand this point very carefully. If x squared is not equal to 2 has no rational numbers, it means that rational numbers are not enough for modeling the concept of physical quantity. It does not mean that physical quantities do not exist. And all the reasoning which I gave you about difference between physical object and mathematical object is necessary for avoiding to believe that physical reality is not existing. Okay? So the good mathematician knows that his models are his brain's invention, and the set of his brain's inventions is not coinciding with the set of real objects. Okay? Now, however your mathematics may be complicated, reality is always more complicated. Okay? Probably Shakespeare once said something like the reality is much more complicated than your dreams wanted to say something like that. Okay. So, it is therefore crucial to be able to understand when a metric space is complete or not. Okay, because non-complete metric spaces are mathematical models not good enough. Okay? By the way, this story, I spoke about Newton approximation system method, which, by the way, is not always converging. You see, if you must divide times f prime of x1, and if by chance you start from here, you are blocked in the middle. Okay? This is another instance of the tragic situation in computational analysis. When you try to divide times 0, you are lost. Your algorithm is blocked, as we said already in the last lecture. Okay, so it is clear that we really need to build complete metric spaces. Okay, now there is a very good news. This good news is the following. Every metric space can be completed. So if you have in your hands a metric space with some holes, then you can complete it. And I was telling you very quickly in the last lecture how to do this job. Now I will give you more details, and then I will give you the exact pages of a book. We will send you an email in which a book, that one of Lebedev, with exactly the pages where you find the demonstration of the theorem I'm simply describing quickly, is available with all details. Okay. But the idea is that which was suggested by your colleague engineer. Let us try to make the closure of our set. However, the closure can be calculated if you have a space in which your set is embedded. Okay, so we must generalize a little bit the reasoning. So, actually, S bar is a new set of objects. And we must embed S inside S bar. So, first of all, we must prove that every element of S can be identified with an element of S bar. Okay. Then we must build a metric in S bar. Let's call it D bar. So that we have S bar, D bar is another metric space. D bar, S bar, D bar must be complete. Okay. And when you take S1 belonging to S and S2 belonging to S, and you consider them as elements of S bar, you must have that the distance between S1 and S2 with the old matrix in S is equal to the new matrix D bar of S1, S2. Here there is an identification hidden. So if you want to be a very precise mathematician, you can introduce an immersion E between S and S bar, which identifies the elements of S as elements of S bar, so that here you can write I of S1, I of S2. Okay? So what we want? We want to take your set S. You build another set S bar. You identify every element of S with an element of S bar. You extend the matrix in S bar, okay? But this extension must give you the old matrix when you consider the elements of S. S bar, D bar form a complete metric space. And last, but also very important property, S is dense in S bar. Which means that every element of S bar is the limit of a sequence of elements of S. So, this means that for every S bar belonging to capital S bar, there exists a sequence Sn of each Sn belonging to S, for which limit of Sn is S bar. If you think slowly, because this is very useful, if you think slowly, the set of real numbers is such a complete matrix space. It completes the set of rational numbers. How this happens? If you remember, every real number is the limit of a sequence of rational numbers. So, the set of rational numbers is dense in S bar, in the set of real numbers. Okay? The distance between two real numbers is R1 minus R2 bar, absolute value. And when you consider R1 equal to Q1 and R2 equal to Q2, the new distance is equal to the old distance. and a rational number is a real number. So, what we have in mind? We have in mind a process which generalizes the construction of real numbers starting from rational numbers. This is what we have in mind. Okay, so I think that up to now, what I'm telling you should be more or less familiar and clear for everybody. What I discovered is a little bit difficult, especially for a question I got from somebody among you last minutes of the last lecture, is how clear is in the mind of the students of this audience the process invented for defining S bar. Okay, so I think it is worth that I give you as many details as possible about this construction, which is essential for understanding the theorem. So, the idea is, I start considering the elements S1, Sn. So the sequences of elements of S. Okay? Then I can build the set of Cauchy sequences. So I have the set of sequences. Sigma. Sigma is the set of all sequences of elements of S. Then I restrict my attention and I consider only the set of Cauchy sequences, which is a subset of sigma. Okay? This is a particular subset of the set of sequences. Now, we move a little bit a step. A real number is an object characterized as a limit of Cauchy sequences of rational numbers. How many Cauchy sequences of rational numbers are converging to a given real number? Many. You think about square root of 2. Okay, I can build a sequence of Q1, Qn from approximating from below. I can build a sequence P1, P2, Pn of rational number approximating from beyond. But what can I do? I can choose Q1, P2, Q3, Q4, so I can jump back and forth, and I'm still approximating square root of 2. So there are many equivalent Cauchy sequences which are approximating square root of 2. There are many different ways for approximating square root of 2. So I must be ready to choose in the set of Cauchy sequences those Cauchy sequences which want to approximate the same element in the complete metric space which we want to build. Okay? So this has to be clear in your mind. If you have this clear in your mind, then you can introduce a equivalence relationship between Cauchy sequences. You say that the sequence Rn is equivalent to the sequence of Sn if we say it in words, if they want to approximate the same element in S bar. Okay? How do you think we can characterize the fact that two Cauchy sequences are approximating the same element of the completed set? The limit for n tending to infinity of the distance of Rn and Sn must go to 0. Sn, you know, this is a definition, but it is a consequence of our heuristic procedure. I want a set S bar. This set S bar must be made of elements which can be approximated by sequences of elements of S. Two Cauchy sequences want to approximate the same element. If they both go to the same element, the distance of Sn and Rn must be 0. This is clear, right? So this is a good definition of equivalence. Okay? So now, I hope you are familiar with the concept of class of equivalence. Okay? CS can be represented as the union of the I'm asking length now, equivalent sequence I is a set of indices. So I have a partition of the Cauchy sequences. Look, this index is not finite. In general, it is infinite. Okay. So I take my CS, and this CS can be subdivided as the union of subsets. Okay. ESI intersection ESJ, if I is different from J, is empty. So you have subsets of CS which have empty intersection, and their union is filling all CS. Okay? And each ESI is made by all the Cauchy sequences which are equivalent to one specific Cauchy sequence.
So it's a disconnected set.
There is no topology in this. So, you have that, I know, you think about the plane, and you think about a partition of a subset of the plane in a connected way. You are right and you are wrong. I try to explain you. If you have a subset, okay, I want to. This is a required abstraction. So you need. So imagine that you take this partition. You have in mind this partition, and you say that this point is equivalent to that point because I can go from here to there with a curve which is connecting them. Okay? But this is a possible partition in a particular set. Okay? I call, if I have an abstract partition, what is an abstract partition? I have a set A. The set is union for I belonging to a set of indices of IA, and IA intersection IJ is empty when E is different from J, then I have a partition. I give you an example which kills your idea of partition. Consider 0, 1, the interval of real numbers. Then you consider the rational numbers inside 0, 1 and the set of irrational numbers inside 0, 1. The intersection is empty. The union makes 0, 1. Between two rationals you have a rational, two rationals you have an irrational, and between two irrationals you have a rational. So there is no connection of any kind. It is a partition. You are cutting your set into subsets. Okay? That's all. I cannot even imagine what is a partition of a set of Cauchy sequences into the set of equivalent Cauchy sequences. I cannot imagine a drawing for this. This is an abstract definition. Okay? But computationally there is a meaning for this. Two Cauchy sequences are equivalent if at the nth step of one and the nth step of the other one you get two elements which are close, and bigger is n, smaller is that distance. So it has a computational meaning, this definition of equivalence. Okay? And don't think anything else. Okay? You are adding structure to your ideas which is useless. In the concept of partition, the concept of connection is useless. Okay? Mathematics is getting rid of useless properties, keeping only the right properties. Those who are really essential. Okay? Okay. So, in ESI, you have all Cauchy sequences which are equivalent to a given Cauchy sequence. Okay? So you can choose one of these sequences. We call it X and I. We write brackets for meaning. Consider all Cauchy sequences which are equivalent to this one. And this is ESI. Okay? So you can take one representative of the class of equivalent as a good example of the element ESI which you are introducing. Okay? Now, the set of all ESI is S bar. So S bar is the one element. So S bar belongs to, small s bar belongs to capital S bar if and only if S bar is equal to the equivalence class of a certain Cauchy sequence. Now, this is exactly, if you study in your books of mathematical analysis, this is exactly what is written in the construction of real numbers starting from rational numbers. We are using only the concept of distance between two elements of S. Okay, I know this is difficult, but I got my master and PhD at the University of Napoli, and these ideas were developed by Renato Cacciopoli. Many of these ideas were developed by Renato Cacciopoli in a more or less original form. You know, Cacciopoli was a very strange person. One of his best, most advanced theorem, the mythology, the legend says, has been proven on the towel of a pizzeria in the quarter of Vomero in Napoli. And Banach has proven it 3-4 years after. But you know, Cacciopoli did not worry about writing a paper about it. He wrote the theorem of the towel, and it is said that the pizza maker placed this towel in a frame at the entrance of the shop. Cacciopoli, there is a movie about him, so if you go, the movie I think the name is History of a Neapolitan Mathematician, something like that. It is interesting. So all gossip about him is more or less politely said in that movie. You know, he was a very strange man. He went to Germany, he gave 20 talks there about a theory, geometric measure theory, he was inventing, and he had never written any paper about it. So German mathematicians started writing papers on Cacciopoli theory, citing the seminar by Cacciopoli. This is typical attitude of South Italian intellectuals. It didn't work. Also, the George was more or less the same. Why I'm telling about Cacciopoli to you now, not only for stopping a few minutes, but also because it is due to Cacciopoli a very clever observation. There is also another way for defining real numbers, not as Cauchy sequences, which is historically more ancient. Okay. You can introduce so-called Dedekind sections. You take, this is useful because in this way you exercise your brain with the concept of partitions. Okay? Consider the rational line. So the line of rational numbers. Okay? So here you are drawing only rational numbers. Okay? Then a Dedekind section is what? You take Q1, Q minus, and Q plus. A subset of Q. Q minus, another subset of Q plus. Then you consider Q minus union Q plus equal all Q's, all elements of Q. So you have a partition of rational numbers in two subsets. Okay? If you have Q minus belonging to capital Q minus, and you have Q plus belonging to Q plus, capital Q plus, you impose that Q minus is smaller than Q plus. So in one subset you have all rational numbers smaller than all numbers in the other element of the partition. Okay? And, very important, for every n, there exists a Q minus n and Q plus n, such that the absolute value of Q minus n minus Q plus n is smaller than 1 over n. So you take a rational number here, another rational number there, and that distance is as small as possible. And you can define the set of all Dedekind sections of Q as the set of real numbers. Okay? Now, why I prefer the definition by using Cauchy sequences? I want to use the smallest possible mathematical structure of my metric space. When I consider Dedekind sections, I need to know what it means that one element is smaller than another element of the initial space. So I need a relation of order in the set of rational numbers. I need a order relation in the set, in the metric space from which I'm starting. And I don't want what it means that C0, a function is in C0 is smaller than another function of C0. It means something sometimes, but if you have this function and this other function, you have no order relation between them. So if I have a set of functions which is a non-complete metric space, I cannot generalize Dedekind approach. So I don't like it. Again, mathematics is the art of finding the minimal amount of properties which are sufficient for building a new structure, a new idea. Okay? Recall what is a Cauchy sequence. For defining a Cauchy sequence, you need a metric. Period. You don't need anything anymore. Instead, for building Dedekind section, not only you need a distance between elements of Q, but you need also an order relation. Okay, so here I'm telling you that Greeks were very clever. They invented powerful abstract concepts, but they are not teaching us everything. In order to generalize the concept of metric space, which is complete starting from a given metric space, you cannot use the old good ideas from Greece or Hellenistic science. You need to invent a new way of building, which is the one I am suggesting you here. Of course, Caccioppoli would have said that he is a philosopher of migration, so he's continuing the Greek tradition, and he could probably agree with it. Okay, but this is more or less a joke. He's much more modern than Hellenistic scientists. Okay, now I gave you all the details of the construction of the complete space. But I must leave you as an exercise, because this is not a class in functional analysis. I give you as an exercise to complete the proof. So, please write down all the questions for the exams I'm giving you. I gave you some compulsory questions. So, up to now, I told you 2 questions which for sure will be asked as an oral part of our exam. Now I give you, okay, we will take, don't panic, we'll write down. Okay. Anthony is writing all of them. Right? The question which I leave as your possible choice, it is not compulsory. If somebody wants to impress me, showing that he studied a lot, so getting a better note, he can go in the book I give you and read the whole theorem. And if he's ready to talk about this theorem, he will start with a better. Okay? So I give you the idea. Because now I defined S bar. Okay? An element of S bar is an equivalence class of Cauchy sequences. First thing, I must embed S inside S bar. How can I do this? I take an element S in S bar and I build a wonderful Cauchy sequence. Sn equal S for every n. It is the constant sequence. Okay? Then I take the class of equivalence of this Sn. Because, my dear friend, I can also write Sn equal S plus 1 over n. This is another Cauchy sequence of elements of S, and this is equivalent to the other one. The only way for understanding a theorem is studying carefully its demonstration. You have no other way. To understand all technical details is equivalent to understand the ideas. Okay? The old exam Italian style was this one. You go at the blackboard and you must talk 2 hours about the subject of the exam. And the professor is allowed you to ask every question. Okay? In this way, we selected the best scientists in history of humankind. Then they changed this procedure, and the quality of our students is going down and down. Okay. This is typical of Italy. When we have success in something, we modify it. Okay. Useless to say. We must change it. Okay, so I can also write this other Cauchy sequence. So you imagine there are infinite Cauchy sequences you can build. Okay? So, I am embedding S inside S bar, choosing the class of equivalence of Cauchy sequences which are equivalent to the constant sequence Sn equals S. So, this is our embedding, I of S. Okay? First step. Then we must build the metric inside S bar. Okay? How do we do this? Look in Lebedev. Now I tell you a story. I was teaching, I gave a talk, I gave a lecture in Virginia Tech 20 years ago. And I had a class of 10 students. 2 of them born in the United States, 8 of them born in other countries. Of course, the 8 born in other countries were much better than the 2 American born students. And in the class there was a Russian who had studied for a master, for a bachelor in Russia, and was studying for the master in the United States. And he gave me this book I'm giving to you now, written by his Russian professor. And we studied the theory of being, and during the discussion, I understood that the 2 Americans did not know anything about the completeness of a metric space. So we made a part of the class for them about this subject. So it was very interesting. The Russian student was teaching to the American students this theory. This was very interesting. And what is very difficult to understand is that the S-bar complete space has as elements the set of equivalent Cauchy sequences. This is the really crucial point of the construction. Okay? So, what is the bar of S bar 1, S bar 2? You take one element of S bar 1. It is a Cauchy sequence. Okay? So we call it S1n. N is the counter of the sequence, and 1 is the name of the first element, S bar 1. And then you take S and 2, an element of S bar 2. These 2 are elements of S, capital S. So you can calculate this distance. Okay? We define in this way, limit for n tending to plus infinity of this distance is the distance between S bar 1 and S bar 2. When giving this explanation to my students in the United States, I remembered what my professor, she was a lady, very clever. I even remember her name, De Forgellinis. She was a very clever teacher in high school. She said to me, how do we want to calculate? She had been student of Cacciopoli, so she said the distance between square root of 2 and square root of 3. How do you want to calculate it? Easy. You take a sequence of rational numbers converging to R square root of 2. You take a sequence of rational numbers converging to square root of 3. And you calculate distance of Rn. This converges to R square root of 2 minus Sn of square root of 3. This limit for n tending to plus infinity. This is what you are doing every time when you use your computing machine. When you write square root of 3 minus square root of 2, what is doing your machine? It calculates this element with 8 digits, this element with 8 digits, makes the difference, and you get the approximation of the distance between square root of 2 and square root of 3. There is nothing new. It is a little bit more abstract, but it is what you are doing. Okay? Now, it could be that somebody among you is a good mathematician. Anthony. Anthony is rather clever. So I expect from him the following question. If I change the representative in the class of equivalence, if instead of taking S1n, I take another sequence inside S1 bar, there are many of them. Is this distance changing? Lemma. You find it in lemma. This limit exists and it is independent of the representative Cauchy sequences. Okay? Let's go back to this definition. Am I telling you in your computational algorithm how to calculate the approximating sequence of square root of 2 and of square root of 3? No. This limit is independent of the chosen sequence approximating square root of 2 and square root of 3. So you already know these things. You know something without knowing it. Okay? Very well. So now we have the definition of the distance. And this definition can be proven is independent of the choice of the sequence. Now there is the tricky part of the demonstration. S bar is complete. This is very tricky. Okay? So I simply give you a hint. Then I ask you to go and to read the demonstration. It is a part of the exercise to find in the book where the demonstration is. But it's very easy. You look for complete spaces and you find it. Okay? Now you have a sequence of S bar 1, S bar n. Okay? So you have a sequence of class of equivalence of Cauchy sequences. I know you could believe that we are crazy, but this is the construction. So I can take a representative of S bar 1. So I take S1, sorry, let us place the 1 at the top, so it is better. So I have S11, S1n. Okay? Then I have S bar 2. It is S21, S2n. then I have Sn1, Sn, and so on. Okay? And all these are Cauchy sequences. And this sequence is Cauchy. So I have that D bar of S bar 1 and S bar K, this is smaller than epsilon. If n, small n and small k is big enough. Okay? So what we can do here, we can choose 1 over capital N, and we choose S bar N and S bar K in such a way that their distance is smaller than 1 over N. Okay? Now what is tricky, and I will not try to do it here, is this. I choose here in the first element one element. Okay? In the second Cauchy sequence, I choose another element far enough. Okay? In the third, another element far enough. Okay? Look, this is a double sequence with 2 indices. Actually, I was wrong. Here, I should have chosen, so correct it as M. Okay? So, if you go, you find that I can build a Cauchy sequence S hat of n, choosing for every sequence, for the sequence n, an element which is far enough, which I call M of n. Okay? Then I must prove first that S hat of n is Cauchy, and second that the class of equivalence of S hat n is equal to the limit of S bar n. If I have a sequence of real numbers, how am I approximating the limit of this sequence of real numbers? I take a rational number from the first approximating sequence, a rational number out of the second approximating sequence, another rational number out of the third approximating sequence, and so on. So, the first real number is approximated by rational numbers. I take one approximating number, rational one. The second real number of the sequence is approximated by another sequence of rational numbers. I take a second element out of this, and so on. If I go here far enough for every step n, my new sequence of rational numbers is approximating the limit of the sequence of real numbers from which I'm starting. Okay? So you understand that all this is computational analysis. This is the fundamentals of computational analysis. Okay? Okay, I think that for today I was exploiting your abstraction capacities even too much. Okay? So we'll send you the reference. Okay?